we'll leave this in for now, just in case, we want to make a change to the rules. This function right here, takes in that, we have the leaders, and then does what we did for the whole class. But there's the consistent thing of if someone makes a shot, if you made your shot at 10%, the next shot has to be at, let's say the increment's 1% less, the next shot has to be at 9%. We could change that to make it, same as 10% as well. But this right here would go on to simulate an entire game. So, for this class right here, we could do simulate game, and we have, you started at 10% chance of making. There are, I'll make sure there are 9 of us, and we will say the increment is by 1%. You can go 1% further. Game, and in this case we have player 8-1. We also have
The screen is no longer.
The recursion broke out.
the recursion is on okay, that's back. It's back. It's back. Lovely. Okay. Well, not much happened. So if we set this to true, we can see what happens in this situation.
What?
We see a lot of misses. Player 9 makes it from 9. Player 10 with Bryce, there's only 9 players. So, you made it. Basically, this is the situation. Everyone missed it. Professor Miller then wins.
And Professor Miller is able to take the basically.
Yeah, the layup, which in the mod, we're going to see the layup is 100% optimum because all our good players. It's, pretty reasonable. If you're the last player, give yourself a shot here. You're going to make. Maybe the pressure gets to you and you miss and you go through it all again. But yeah, in this situation, here we have that. We can go on to simulate just a single game. And we can, modify, let's say you start at an easier shot. You start an easier shot, and we see a lot more, makes. You made it from 70%, player 2 makes it again a little bit further. 2 misses, or make, and then player 9 misses. So player 8 wins. So you can kind of, play around with these, starting values and, simulate a single game. But this doesn't really give us insight as to what is the optimal thing. You don't want to simulate a bunch of games. We'll go and copy over some right here of where we're going to go and try a bunch of games. And this function right here, I can go many games. Let's say let's try 1,000 games and starting at a real easy shot, 70% on the making. And as you point out, at this point, let's just have the increment easier where the last made shot from the position goes on the win.
Do you need the number of people first?
Huh?
Before the 0, do you need the number of people?
Yes. Good. So now we have 9 people in this game. So if we go like this, we're gonna get a bunch of guys, but here are the people that go on the win. We can make that a little clearer by creating a table of it. And these would be the results out of 1,000 games. In this scenario, player 3 only goes on to win 1, player 4. Once you were 5th, you should have only won 15 out of the 1,000 times, but you beat the odds. And this, is if everyone's going at that same percent. But you started at what, 10% was the initial. So let's see what odds that was given. A little better, because you're not immediately giving away a 70% shot. You shoot with 70% odds, it's likely someone else is gonna go right on top. So here we're still seeing big advantage for these last players, especially 9. It's kind of I don't know why you decided to move to the end, read the paper before something, but yeah. So we can kind of go on to see that it's beneficial to the end. We're still trying to figure out ideal strategy. And I guess one caveat to this function is we're not really allowing for players 2 through, the last player to, modify their strategy. We're saying shoot from the same point as the
Right.
first person. We're only counting, everything else is fixed, except for this variable that we have at the beginning, right here, that describes what player 1 starts at. And that, makes it a little tricky. Like, we can't run this and figure out, optimal strategy for everyone. But one thing we can do is this actually, if we modify this first value and, test it at, let's see, we test it at 1% or 2%, all the way up to, a 99% shot, that we can figure out how many times you're going to win, because everyone else after you is trying to beat you. They're shooting at, no closer than where you were. So it kind of, gives an idea of what player 1 ideal, shooting position is. So let's see if we were to, vary the amount of here. We were to go on to vary the amount. So right here, we're looking at how many wins you're going to have as player 1, modifying from, your initial probability of 0, which, like, why are you going to take a shot that you have 0% odds of making? We might as well put that in, and then it'd be kind of dumb to, make one that you guarantee to make, because the next person can just make that. But this whole range in between, anybody, 1% of the time, might give us, a rough estimate of where you would want to shoot from. So we're gonna do this, and it takes a little bit of time right here, but not a lot. There we go. Playing 1,000 games at each position,
Okay.
and then counting how many times player 1 actually won. We can go on and plot that. As you can see, kind of gives us a little bit of this, weird figure. There's a lot of variation because it's 1,000. We're going to get close to a mean, but we're not going to get,
Can you enter with 10,000 while you talk about the plot? Or would it just
go on to
okay?
10,000
Okay.
later on. But yeah, if you run it over 10,000 instead, it's going to smooth it out a lot. But 10,000 is going to be pretty slow. So let's restrict it though to like 0 to 0.2. That right here, we can change this to 0 to 0 to 0.2, and let's go by 0.5%. 0.5% of the time, we'll do 10,000 repetitions. So this right here is going to give us, a little cleaner window into just where we'd likely to find the maximum amount of games that you're going to win as player 1. So we'll run that again, and right here, a little slower, but thankfully, we're sticking to a tighter window. So this right here takes just a little bit to run.
Out of curiosity, when you have the program running, as soon as somebody after player 1 makes a basket, does it immediately abort?
What do you mean in this one?
Right. So you're trying to figure out what fraction of the time player 1 wins.
Yeah. See, we could have like modified.
So you could actually speed up the code a little bit by aborting it as soon as somebody else. Yes.
Yeah, that would be definitely a good way
To speed it up.
Optimize it a little bit. But even here, right here, we go like this. This kind of actually, we're seeing something a little clearer, and it's in this range right here of 0 to 0.2. And so one thing we actually can do is there's still a little bit going on. What if we fit a polynomial model to it, just give us a clear image. So right here we're fitting a 2-degree polynomial, 3-degree, and a 4-degree polynomial. So this first one, you get something kind of approximating it, but you get a little closer with a few more. So like there, 4th degree looks pretty close. As we add more, it's not really changing it a substantial amount, but we're kind of seeing right here is the peak of what we're looking for. So let's see how let's figure out what that value actually would be. So we're going to look at 2,000. Which one is the maximum from this 4th degree polynomial, which is in purple. 4. And let's see what it looks like. So 0.07, it seems, is the point. That looks about right. 0.07 is where you actually be taking this optimal first shot, where in a game of 9 players, that's your best odds, more or less. And obviously it's done by increments of 0.05. So a little bit of variation, but gives an idea of where that first player goes. So that actually, is helpful, but just for player one. We now know player one, to maximize the amount of games they're going to go on to win, should shoot at this value. So then the idea is, how do we compute this for the rest of the players? And one way to sort of think about it is, if, let's say, player one makes their shot, player two should shoot at that value because they have no other choice. But in a game of less people, you don't need to go back as far as possible. So if they miss, it now becomes an 8-player game. With an 8-player game, you don't have to, except you have to pour 1,000 people, you're gonna want to take a really risky shot if you're that first person. Where there aren't that many people, you're going to go closer. So the less people remaining, the closer you kind of can take a shot and hopefully get away with it. So we can kind of take a look at 4, let's say, player in an 8-player game. We could look at first player and investigate like where they should shoot if the previous person had missed, because then it's just an entirely new game. Their player one missed, so you kind of ruled them out of the game. So it's pretty easy to replicate that somewhere in here. This, I guess now that I look at this right here, this was a 14-person game, right? So I forgot to change that. 14 just because it, the game itself and it should have 14 players. Right. So, it's up to you guys if you always want to, keep it with the 14 that we saw in the game or 9. That's in this class.
So let's keep it at 14, because if you've got 14 in the other places,
it's bound to copy something.
Yes.
Okay. So I'm gonna make a line right here. So this right here is, let's see, at the 13th. So right here, I'm gonna go back, step back a step. This right here, all this graph is for 14 players. So if you're the first of 14 players, you want to shoot, there's probably have 0.07 or a 7% chance of making it, which isn't great. That's kind of a risky shot, but that's where you're maximizing because everyone else is going to shoot at that point or closer if you miss.
Now, 7 times 14 is almost 100.
7 times 14. Yeah. So that it gives us a little insight, but don't worry, we'll get there.
Well, this is a different problem than is in the paper, so I have not seen this one.
Yeah. So yeah, there's kind of a little sneak peek at the significance of 0.07 as it against the amount of people in the game. But let's look at 13. We do a similar thing as before. You get a general shape. Again, looks kind of similar, still pretty yucky. But let's restrict the window to a little bit smaller. You get something about the same. And so again, like this isn't super effective to like do this for everyone individually. So I think an easier way to approach the problem is to take a look at, or is to run this all in a loop, as opposed to copying and pasting things over. We get something right here. If we were to fit that, we get last one was shoot from where you have 7% odds. This one we're shooting from where you have 8.5% odds. So when you think about this intuitively, kind of makes sense. If there's less players in the game, you can take a little easier shot than if there were more. That player who went first of 14, if they shoot first, they win the most when they shoot from 7%. In a smaller game with, or I'm saying, sort of 14, in a 14-player game, go from where you have 7% chance. If you're a 13-player game, that first player choose from a little bit be repeated far less likely. So we've done this now for all, or for players 14 and 13. We can from that now for values 14 through 2. as it gets smaller and smaller, look at how to do this function right here, this max quantile, essentially is repeating what we did that first go around, where you get a general rough estimate, and then basically where we find that max, and then a window of 10% either side. So if we find the max of that first function right here, we find the max to be right here, which is what was that 0.15. It would be creating a window on either side from 0.05 to 0.25, just to give us a little quicker, because the mean or the maximum is likely going to fall somewhere within that window. There's no need computing these ones, no need computing that one. Not that this function does. This find optimal is what we've been doing the whole time, finding the ideal point for these things to run. So like I did before, we're going to run it, and this one right here takes a little bit, but kind of a good segue into why this paper actually is pretty fun, because unlike if this was just looking like the game of basketball, there aren't really any other games that have the exact same set of rules that are basketball. Whereas this is was a case of basketball and shooting, taking shots from various points, but it's not necessarily only applicable to this. Like this sort of analysis. You go to different things. Like off the top of my head, I was thinking of, I don't know if any of you guys saw Squid Game. Probably some people saw Squid Game, where they have some game, I think in the later stages, where the people are given a random number and they have a similar thing, but instead of taking shots, it's jumping onto these like little steps of glass, where if some of them are reinforced glass, some of them are glass that you break through, and so you have the first person do they jump on that one, or they jump on the next one? If they jump on the wrong one, it breaks, they fall through, they die. So it's not as nice as this game, but similar thing. You kind of take a look at what's the advantage of going last. You last have everybody to go before you, give you an idea of which ones to go on. Whereas the first person, they're just kind of going by chance, and depending on how many tiles they have to get through or something, then it becomes more just more of a disadvantage to go first, or even more of a disadvantage to go first. It's always going to be detrimental to go first in relation to the person going last. But it's kind of an interesting thing. And, there are other games where you need the first person to kind of like discover the path. The last person just follow the footsteps of the previous. So it's kind of a cool idea that can be applied beyond more than just this 1980s basketball competition. I don't know if you guys or can think of any other sort of games or scenarios where there's benefit to the last person, first person.
I was thinking a little bit about the pirate game.
What's that?
Did we do that in this class with pirates and dividing up 100 gold coins?
Oh, yeah, we did.
Right.
Yeah.
And so just, what is your strategy based on how many people are coming? I just, it's this idea of trying to reduce to a simpler case, that as soon as the first person has missed, we now have a game with one fewer people.
Yeah, and kind of like that. And especially if you start to factor in the value of something. With this, the last person that makes a shot gets $1 million, but you have the case of the pirates, how to divide the money.
Right.
You can kind of look at what's the odds of someone going to win. If you're the first person and you're going to take a shot from 7%, then it's not a good fortune player, but if you're the first person in 14-player game to take a shot from 7%, you're most likely not going to go on to win. So can you make a deal with players behind you to go from an easier spot to make those changes? And if you throw money value, then it's a little more exciting, a little more interesting.
So I mean that would be great if players 1 through 13 had make a deal, and we'll split the money.
Yeah. The thing is, I guess the last player always gets a say, because they can't really be factored out.
So for someone who's not presenting, if there's 2 players, where should player 1 shoot from?
Free throw line?
50%. Because if you miss, the other person's going to win. So you don't want to shoot where you have less than a 50% chance because you can guarantee a 50% chance.
Yeah, which, might be a good segue into, let's take a look at what the optimal points are. A little rough, but we're seeing right here that first person in a two-player game shoots at, 0.52. And, a little bit of, the heads up that things are, not quite as, ideal because, we're looking at, a simulation of 10,000. It's close to the mean, but not as true as we would like. So then, if we were to slide all over the place, let's see. So now we kind of have established, where these people should go on to shoot. What if they all know this opposition? What are the odds of actually going on, or how many games are they running? Player one is shooting from, in this case now it says 70 or 7.5%. Close enough. Especially that, like, do they win then 7% of the time, or do they win a little more, win a little less? This just says where they should shoot from. And
well, before you do it, do you think they can win more than 7.5% of the time?
No. Well, good thing we can go and have some code and find out. Let's see, we have that. This right here. Let's now, simulate an optimal game. And this optimal game right here. That there. And what this function does right here is, you have the current lead, the current leader, initialized, but then the optimal shot is basically that position that they had. That's like stored in reverse order that we found from this previous function. Find the first person goes at 0.5. Spoiler, I guess the third person goes at or third to last goes at 1 over the fourth to last.
Okay. And there's no danger that somebody will be shooting from closer than predicted. Or further, that if you're the third shooter and the first person and the second person both make their shots.
No, you go from the maximum.
You go from the maximum.
Sort of like the minimum. It's the least likely one.
Right.
Right here, yeah. This is where it is.
There it is. Okay.
Yeah, it's the shot position. You have your position. It's your optimal position. That's your optimal. If everyone before you missed.
Right.
If someone had made it,
then you go from where they made it.
Where they had made it.
Right. Exactly. Yep. Exactly.
So we write this, and here's an optimal game right here. By chance the seventh person won, which isn't super likely if we run it again. 15, 14, 13. You've seen a lot of these last players going on to win in this optimal strategy. So again, it's like, let's simulate this 1,000 times, or not 1,000, 10,000, just because this isn't a super expensive function. It's going through just
right.
It's not 1,000 is the max increment. We can just say, all right, let's see, given those arrays that we found before, what do we have? We have winners. This right here, again, a big value, but we can, let's just make it histogram of it. We're seeing something right here. This right here is because it's grouping, 0 and 1 together. That's what we have going on right here, and just how R displays it. But we're given a bit of an image of how many times this player goes on to win out of the 10,000 games.
Does R give you a simple command to change from frequency to percent for the?
Well, we actually just write that out like table of winners divided by 10,000, and here's what we end up getting for
okay.
Frequency. We're seeing these percentages right here of how many times this player is going to win. We're looking at player one. Player one actually is only going to win. This says right here, based on the simulation, about 2.5% of the time. Not great odds. 14% game. Whereas also I'm sitting right there. If there's 14% game, has those odds of going to win. So, a little bit of, well, not a little bit of pretty big advantage
right.
going first. And so right here, we've kind of answered the question of, what are these likelihoods of going on to win given these positions that were assigned in the game. I'm going to return the presentation for a second. Share my screen again. Okay, so now we've simulated all kind of seeing a way to go about figuring out these percentages without actually even using any math. We're just running the game, seeing what we get from it, how the paper actually going into it. And I'm not gonna stay here and try to explain the full math just because a little more complicated I understand, but give you a rough idea of how they went about it. So right here it's looking at the probability of each shooter and similar idea where they're going to have some optimal position, but it's going to be from either the previous best position or their new optimal position. That's kind of the idea that, in a player with, or in a game with less players, you don't have to go as far back. So you're going to have to either choose from, this furthest point that you're most likely to still win, or if your hand is forced to shoot from where the previous person before you had made that shot. And so right here, you get this idea that, as we do with that first example, if there's two players, that first player should shoot from 50% odds of making it, because if they make it, then that next person, the odds are, at best 50-50 that they kind of repeat. Anything less, if you shoot at 30%, you're less likely to make it, they're going to win. Because if you miss, player won't, the last player is going to win. But if you go from a shot that's more likely to make, they're going to be able to repeat that's more likely than make a shot. And so then, you continue on. This right here is the overall summary of the paper, where, and the paper went out where the odds of missing a shot. Missing a shot in a 14-player game, they should take the shot where the odds of missing are 13 out of 14 players, because that first player of the 14 makes the shot, then the odds are that none of the other people make it. So this right here, keeps it a little easier to understand where, player N shoots, the odds are making, they should, given the fact that they get their choice to shoot from one over the amount of remaining players. And then, the odds of, if you're playing by these optimal positions, the odds of winning can kind of be described right here by, sum of the odds of player one, or player before somebody makes the basket, player K makes that same basket, all players have to miss this first one right here. Plus, the odds that you as player K make the basket, and then all people miss the basket. This right here is, a little bit of the probability of, probability of jamming the basket. Right here is what 1 over n. The optimal strategy that they make that shot. And then 1 over n. A little bit of math pulls up from above that I'm not going to try to explain because the paper explains it better than I do. You end up getting the math kind of derivation of this thing. So here's what they found. They found something that looks pretty similar to what we found. First player has 2.7% chance of winning, whereas the last player has 23% chance of winning. What's that? That's, I don't know, 12. It's 10 times 12. Yeah, a lot more percent. Better odds to the last player. Shooter 1 is shooter 0. Last one first, different indexing. So what did we find? This is what we found. And this one actually is, just one of the ones I ran previously. But if you look at this, there's, nothing off by more than 2%, I believe. And, we're finding that, the last player 23% of the time is going to win. They found using that on this 23.2% of the time. And, kind of cool that we can come to the same solution by a completely different technique. But one thing though about doing the math approach is it kind of gives you it's one player for me. We might not necessarily see that from that array of values it's close enough to 1/2 and 1/3 is the optimal shooting positions. But other than that, we get pretty similar things. So
Although if you did a log plot,
a log plot in terms of,
well, if the optimal place is 1/n, you'll see a very nice relationship.
okay, yeah, if you actually plot those up like that.
Right.
Yeah. So yeah, you have to play around with those
Right,
boundaries.
but that's one thing I want you to get out of this class is keep looking for relationships. It's often not clear what's the right way to look at it, but it's there.
Yeah, so yeah, in the simulating version, you play around with it a little, you kind of start to see the pattern, whereas in math, it's right
Yep.
what you're seeing
Yep.
how it is. So 2 different ways of going about it. But gives this gave mathematicians an idea of what are the odds of winning. But sometimes it's not always the case that the most likely person wins. As in our class example, you won. What were the odds of, let's just say it's a 14-person game, but even so, you 5th out of 9 was about halfway through. Half of this, you didn't have great odds of winning, but you beat the odds somehow. So what happened here? Let's see. Right here, the first person make a bank shot, a miss, a make, miss, a make. Everyone else missed. So player 4, which I guess in this actually is player 5. So maybe something for lucky number 5, beating the odds. But yeah, there you have it. Sometimes it doesn't always align, but it's kind of an estimate of what things look like in the long term.
Shout out the first guy. That's
I know.
a good way to start.
He's got 9 shoes. He's like, I'm good. I can win it. But what's 24 feet? That's just outside the point line by 4 feet. And what we found way back that 30%. Like,
With that many people going after you, it's
yeah, he took a shot maybe at had 20% odds of making or something. So the odds are someone makes on top of him, or someone's gonna repeat. So he took a too easy shot.
right.
Still cool that first guy stepped up, makes the shot, but didn't pay off. So yeah.
All right. Thank you. The other thing is, the first player might have had a different objective. He might have realized, I'm not going to win, but I want to look good. I don't want to look